Imagine existing in a realm of unimaginable extremes, where time and space have yet to crystallize into the familiar fabric we know. 1 second after the Big Bang, the universe is a maelstrom of chaos and upheaval. But what precisely would you witness in that fleeting foundational moment? Prepare to journey back to the very dawn of existence, exploring the most pivotal second in cosmic history. To truly grasp this monumental moment, we must first visualize the conditions that define the universe's birth. Our story begins not with a bang in the traditional sense, but with an unfathomably dense point known as a singularity. Here, all matter and energy were compressed beyond comprehension. From this infinitesimal point, the universe began to expand at an astonishing, almost incomprehensible rate. This rapid expansion, known as cosmic inflation, set the stage for everything that would follow. It stretched space itself, laying the groundwork for the vast cosmos we inhabit today. At this particular, nascent moment, the temperature soared to trillions of degrees Celsius. This created an environment hotter and more energetic than anything we can observe or replicate today. It was a crucible of creation where the laws of physics as we know them were just beginning to take hold. In this chaotic, superheated landscape, the universe was a dense, energetic soup. Particles like protons, neutrons, and electrons, which form the basis of all matter, were not yet stable entities. Instead, their constituent parts were rushing about in a frenetic dance. This is the instant when the fundamental forces of nature began their grand separation. The strong nuclear force, the weak nuclear force, electromagnetism, and gravity, all once unified, started to emerge as distinct entities. This separation was crucial as these forces govern every interaction in the universe. The strong force, for instance, would eventually bind quarks together to form protons and neutrons. The weak force plays a role in radioactive decay. Electromagnetism governs light and chemical bonds, while gravity shapes large-scale structures. Their emergence marked a critical step in the universe's evolution. The universe was beginning to differentiate, casting the very building blocks of matter into the void. It was a period of immense energy and rapid change, where the future structure of the cosmos was being subtly yet profoundly influenced by these initial conditions. Every interaction, every fluctuation held immense significance. As we delve deeper into this fiery abyss, the universe was still far too intense for stable atoms to exist. Even protons and neutrons, the nuclei of atoms, had not yet fully formed. Instead, we would witness a swirling, energetic soup of quarks and gluons. This exotic, primordial state is known as quark-gluon plasma. Quarks are the fundamental particles that make up protons and neutrons, while gluons are the force-carrying particles that bind them together. In this extreme heat, they were not confined within larger particles. Imagine a cosmic stew where these fundamental constituents moved freely, unconstrained by the forces that would later bind them. This plasma was incredibly dense and opaque, a testament to the immense energy packed into the early universe. It was a fleeting phase, but absolutely essential. This quark-gluon plasma existed only moments after the Big Bang, a unique window into the universe's most extreme conditions. Scientists today recreate similar conditions in particle accelerators, like the Large Hadron Collider, to study this fascinating state of matter and better understand our origins. But what about light itself? Photons, the very particles of light, were present in abundance during this epoch. However, they could not travel freely through the dense, charged plasma. The universe was effectively opaque, a luminous haze, rather than a clear expanse. These photons were constantly interacting with the free-moving charged particles, primarily electrons and quarks. They were scattered, absorbed, and re-emitted in an incessant cosmic pinball game. This meant that light could not escape to travel across vast distances. The universe was shrouded in a spectacular yet chaotic display of energy. It was a brilliant, glowing fog, where light was trapped within the dense plasma. This luminous haze was a direct consequence of the extreme temperatures and the abundance of charged particles. This period of opacity would last for hundreds of thousands of years, until the universe cooled sufficiently for atoms to form. Only then would light be able to decouple from matter, allowing the universe to become transparent and revealing the cosmic microwave background radiation we observe today. At this stage, conventional notions of time and space have little meaning. But if our hypothetical observer could somehow look around, they would notice a tumultuous landscape. While the universe was largely uniform on a grand scale, slight irregularities existed. These were not random imperfections. These tiny fluctuations in density and temperature were incredibly significant. They are believed to have originated from quantum fluctuations in the very early universe, amplified by the rapid expansion during cosmic inflation. These microscopic variations were the universe's first blueprints. These subtle differences in density meant that some regions were ever so slightly more concentrated with matter and energy than others. These denser pockets would exert a slightly stronger gravitational pull, acting as cosmic magnets. They were the primordial seeds of all future structure. These fluctuations laid the groundwork for everything we see in the cosmos today: galaxies, clusters of galaxies, and the vast cosmic web. The seeds of the cosmos were sown in this initial scene, an unstable but incredibly fertile ground for future complexity and the emergence of structure. Just as our fascination begins to blossom, it is vital to pause and reflect on the profound significance of this moment. If you find yourself captivated by these cosmic revelations, consider subscribing to our channel and activating all notification bells. This ensures you won't miss our continued exploration of the universe's most astonishing phenomena and deepest mysteries. As the first second progresses into the next, temperatures gradually begin to decrease. The universe continues its relentless expansion, stretching space and diluting the energy density. This cooling process is absolutely critical for the next stages of cosmic evolution. The decreasing temperature allows the fundamental particles to slow down sufficiently. This reduction in kinetic energy enables quarks to finally combine and form stable protons and neutrons. These are the building blocks of atomic nuclei, and their formation marks a pivotal transition. At this stage, the universe is still a fierce contender against its own pressure, a dynamic battle between expansion and the gravitational pull of nascent matter. Yet, the cosmic dance of creation persists, moving towards greater complexity and structure with each passing moment. The seconds continue to tick by, and by approximately 3 minutes after the Big Bang, the temperature will have dropped to roughly 1 billion degrees Celsius. This temperature, while still incredibly hot, is cool enough for a monumental process to begin: Big Bang nucleosynthesis. This titanic reaction sparks the first formation of light atomic nuclei. Protons and neutrons, now stable, begin to fuse together under the intense heat and pressure. This process creates the first elements heavier than hydrogen. The primary products of this cosmic alchemy are helium-4, along with trace amounts of deuterium, heavy hydrogen, helium-3, and lithium-7. These elements become the fundamental building blocks, the raw material from which all future stars, galaxies, and planets will eventually form. the precise ratios of these light elements observed in the universe today provide powerful evidence for the Big Bang theory. They're a direct fossil record of the conditions in the universe during its first few minutes, a cosmic fingerprint confirming our understanding of early cosmic history. As the universe continues to expand and cool over the next hundreds of thousands of years, another critical event unfolds. Approximately 380,000 years after the Big Bang, the temperature drops to about 3,000 Kelvin, around 2,700 degrees Celsius. This is cool enough for electrons to combine with the light nuclei, protons and helium nuclei, to form the first stable neutral atoms. This process is known as recombination. Before recombination, the universe was filled with a plasma of free electrons and nuclei, which constantly scattered photons. This made the universe opaque, like a dense fog. Light could not travel freely. Once neutral atoms formed, the free electrons were largely removed from the cosmic soup. Photons were no longer constantly scattered and could finally travel unimpeded through space. The universe became transparent, and light was set free. This ancient light, released at the moment of recombination, has been traveling across the universe ever since. Stretched and cooled by the expansion of space, it is what we observe today as the cosmic microwave background, CMB radiation. The CMB is the oldest light in the universe, a faint glow that permeates all of space, providing a snapshot of the universe when it was just a baby. As we continue to visualize this remarkable phase in the universe's history, we find ourselves drawn into an intricate tapestry of events. From a state of unimaginable simplicity and extreme energy, the universe gradually evolves, giving rise to increasing complexity. The initial quantum fluctuations, amplified by inflation, provided the gravitational seeds. The formation of light elements during nucleosynthesis provided the raw material. The release of the CMB marked the universe's transition to transparency, allowing structure to begin forming. Over billions of years, these tiny density fluctuations would grow under the relentless pull of gravity. Gas and dust would coalesce, forming the first stars, then galaxies, and eventually the vast cosmic web we observe today. It is a testament to the universe's incredible capacity for self-organization. This journey from the first second to the present day is a reminder of both the fragility and resilience of the universe. It unfolds in ways that continually astound and inspire us, revealing a cosmos far more intricate and dynamic than we could ever have imagined. With each passing moment after the Big Bang, as the universe embraces structure and complexity, it gives rise to the stars that illuminate our night sky and the planets that harbor life. Each second teems with the potential for grandeur, a precursor to the universe we inhabit now. Imagine being there, at the dawn of existence, witnessing the raw, unfiltered energy that would eventually forge the stars and shape galaxies. The dynamics of creation, a spectacular interplay of chaos and order, shape not just what will be, but what is already unfolding in the cosmos. The birth of the universe is not merely a tale of the distant past, but a continuous journey that we are all an integral part of. The narrative written on the cosmic canvas is still ongoing, threading through the fabric of time itself, and we are living within its unfolding story. If this journey through the universe's first second has ignited your curiosity, don't let your exploration end here. Hit that subscribe button right now to join our community of cosmic adventurers. Make sure to turn on all notifications so you never miss another mind-bending dive into the mysteries of space and time. Share this video with fellow stargazers, leave a comment below with your biggest cosmic questions. And let's continue unraveling the universe's secrets together.